Hello everyone. This is the third video of your Unit 1 material. I'll probably be able to finish up the material within this video. So the pre-class assignments for the lecture I'm going to give today, which you need to go into my math lab, do these 3 assignments, and then come watch this video, is, so here's your course homepage that you see when you first log in, and you hit the homework button. I want you to click show all and then view all on one page. And I like to minimize, press this little arrow so that goes away so I have a little more room on the page. So as you can see, I have some assignments set up. I have went ahead and made your tests available. So all 4 of your tests, your unit tests, are available, but you have to get every post-class assignment before it done. Okay? So basically what it comes down to is your pre-class assignments, there's no prereq, but your post-class assignments have the prereq as the pre-class assignment. So you have to do this assignment before you can do scientific notation. You have to do order of operations before you can do order of operations in number systems, and so on. So before you can do the interval notation assignment, you have to do these 4 pre-class assignments. Same with the formulas. All the way down to your Unit 1 test, I have every post-class assignment listed as a prereq. So you have to have every assignment done with a 70 before you can take the test. But it's available now. So if you get everything done today, you could take the test tomorrow. But notice it's not due until 6:15 at midnight. Okay, so you still have a little bit of time, but you need to get on it, because our summer school semester goes very, very fast. So today I'm going to go, this is the 3 pre-class assignments, combining like terms, find LCD with numerical terms, and find LCD with variables. And then there's the complex fractions post-class assignment, and then these other 2 post-class assignments that do not have a pre-class along with them. So you notice these 2 post-class assignments don't have a prereq. Okay? So in today's video, I'd like to get through all this stuff so you are ready to take the exam. Okay, so in the previous video, I briefly went over how to solve this problem. When you have a fraction divided by a fraction, you use what's called the keep, change, flip scenario, because these two symbols here, the 3 and the 5, end up being grouped together, and the 2 and the 7 end up being grouped together by doing the keep, change, flip. So you see 2 ends up being multiplied by 7 and 3 ends up being multiplied by 5. So now let's jump in here to this example. I'm going to go through this step by step, kind of slow, just to make sure everybody understands what's going on. Also, if you need more practice on this least common stuff, here is a Khan Academy video, a least common multiple exercise. So it gives you a couple videos and then even has some practice. What is the least common multiple of 2 and 12? And you go ahead and put your answer. So this is another good way to practice finding the least common multiple. Okay? So first I want to just look at the numerator. What I'm going to do first, since both of these are mixed numbers, is I'm going to change them into improper fractions, which we talked about in the very first video. So 6 and 1/3 means 6 plus 1/3. So the way to come up with that is 6 times 3 plus 1. So 19 thirds. 19 thirds minus 2 times 5 is 10 plus 4 minus 14 fifths. And both of these are already in regular form. Neither one are improper. They're proper fractions. So I'll just rewrite it. 11 over 30 plus 1 over 6. Now I'm not going to worry about getting all 4 denominators to be equal, because I just want to get a fraction in the numerator and a fraction in the denominator, and then I can invoke this keep, change, flip property. So 3 and 5, their least common multiple is those 2 numbers being multiplied together. And even if you can't identify the least common multiple, you can always just multiply them together and get a common multiple. You'll probably have to do some reduction at the end, but you'll never be wrong as far as finding a common multiple. Even down here, if you just multiply 30 times 6, you get 180. That is not the least common multiple, but it will still work. Okay? So now, looking at this top, the top of my fraction, this top difference, I want to make sure these have the exact same denominator, which is 15. So I'm going to multiply this one by 5. Whatever I do to the bottom, I have to do to the top. Same thing over here. I'm going to multiply 5 by 3. Whatever I do to the bottom, I have to do to the top. You notice I'm just multiplying these numbers by 1. 5 over 5 is 1. 3 over 3 is 1. So I'm not changing the value. Anything times 1 is just itself. So now let's see what we have. So 19 times 5 is going to be 100 minus 5, which is 95. Over 15 minus 14 times 3 is 28, is 42. Over 15 over. Now 30 and 6, the least common multiple of these two is 30, because 6 does go into 30. So I don't need to do any adjustment to this fraction. I'm going to multiply this one by 5 on the bottom, so whatever I do to the bottom, I have to do to the top. So now I just have 11 30ths plus 1 times 5 is 5 30ths. Okay, now I can combine these fractions. 95 minus 42. Let me go over here and just double check that I did my multiplication correctly. 19 times 5 is 95, and 14 times 3 is 42. So let's do 95 minus 42 equals. So over here now I have 53 over 15 divided by 11 plus 5 is 16 30ths. Now you might look at this and say, well, that can be reduced, which you can reduce it now if you want, but you know, I like to set up my keep change flip, and then I can reduce from there pretty easily. So now let's do keep change flip. So I'm going to keep my top fraction for 53 over 15. I'm going to change my division to multiplication, which I'm going to use the dot, not the asterisk. So times, and then flip. Then I'm going to flip over this bottom fraction. So instead of 16 over 30, it's going to be 30 over 16 equals. Now right here I can do some reduction. 53 is a prime number. There's not going to be anything that goes into 53. So between 16 and 53, there's not a lot we can do, but 15 and 30 definitely have something in common. 15 goes into this once, and it goes into 30 twice. So you see how much that simplifies our answer. If you don't see it right away, you can reduce at the end. 53 times 2 is 106. 1 times 16 is 16. Now, I know these two numbers are even, so at the very least, I can take out a 2. So I just like to take out a 2. I'm not going to worry about anything bigger than that. If they're both still even after I divide, I'll do it again. So let's take out a 2, which I could have done right here. I could have went 1 and 8, because 2 16ths is the same thing as 1/8. But even if I didn't see that, I can divide both of these by 2, and I get 53 over 8. And there's my answer. Can't be reduced any further. 8 goes into 53. 8 times 8 is 64. 6 times with a little bit of remainder. And this number is approximately, let's do it on a calculator, 53 divided by 8 equals 6.625. And if I went in and punched this number into my calculator using parentheses, I could check that I still have this same decimal, because throughout all these operations, the value doesn't change. We've just changed the way it looks. So my final answer is 53 over 8, but 6.625 would be acceptable because it is exactly the same. So I need to get rid of this approximate symbol and put equals, because it is exactly the same. But I prefer 53 over 8. See, since the decimal, I never rounded it, it's exactly the same. Okay. Now we can do the same thing here. So I'm going to use the same method I did above. I'm going to combine the numerators and then invoke keep change flip. After that, I'll show you another method that you can use to solve these problems. So let's look just at the numerator. Let me draw a little line right here so I have a separation. So looking at the numerator, I want this to be x over x, right? Because this is 3 over 1. It looks a little sloppy. Let me write it on the other side. This is the same as 3 over 1. We want 1 and x to be the same. The least common multiple is x. So I'm going to multiply top and bottom by x. Okay. Same thing with this. This is 2 over 1. The least common multiple of 1 and x squared is x squared. So I'm going to multiply the top and the bottom by x squared. So 3x over x plus 5 over x divided by 2x squared over x squared minus 2 over x squared. Now I have common denominators and I can combine. However, 3x and 5 are not like terms, so as far as I can go is 3x plus 5 over x divided by 2x squared minus 2 over x squared. Now I have a fraction over a fraction. Okay, I couldn't invoke keep, change, flip here because I have a split denominator, all right? So you want to have one fraction divided by one fraction. And even though there's multiple things in the numerator, this is still one fraction. So I'm going to invoke keep, change, flip. So I'm going to keep my 3x plus 5 over x. I'm going to change to multiplication. Then I'm going to flip this over. I'm going to do x squared divided by 2x squared minus 2. And that equals, I'm going to have to do the distributive property here. Now I could do reduction, but I'm going to wait till the end to do reduction. And same with this x, it gets distributed. So I have 3x times x squared is 3x cubed. Whoa, let me get a cubed in here. 3x cubed plus 5x squared divided by x times 2x squared is 2x cubed minus 2x. Now for this to be reduced, all 4 of these terms, all 4 have to have something in common. So let's go in here and look. So this term, there's 1, 2, 3, 4. All 4 of those terms have to have something in common for this to be reducible. Notice this has a 3, a 5, and a 2, so there's no reduction we can do amongst the numbers. If I take a 2 out of here, I can't take a 2 out of the top. But one thing they all do have in common is an x. So I can take one x out of each one of these terms. So this becomes 3x squared plus 5x divided by 2x squared minus 2. And there's your answer. Can't go any further from that. All right? And if you want to check, plug in a value for x back here, say 1. Well, you can't do 1 because you get 2 minus 2 in the denominator, so that would give us an undefined value. So you'd have to pick something other than 1. But plug in a value for x, see what you get, what number, plug in that same value for x here, and those values should be the same. So if you plugged in 2 for x, right, it should be the same. All right. Now what I want to do is show you another method. Basically what I want to do is multiply this top fraction by something and this bottom fraction by something so that these two denominators go into it equally. So what is the least common multiple, LCM, of y and 3y squared? Well, the way to do that is to break it down to its prime factors. That's already in its prime factor. This is 3y squared, and this breaks down into y times y. So I can borrow this y, and this y can take the same place. But I have to keep this 3 and this y together. So actually the least common multiple of these two is 3y squared. So I'm going to multiply the top by 3y squared. And if it helps, write it over 1 just to keep your positions the same. 3y squared over 1. Because if I went and multiplied these two together and these two together, you can get 3y squared over 3y squared. So they are equivalent. I like writing it this way because then you keep your levels all the same. Okay. Now let's ask ourselves, y goes into 3y squared. What's left over? That goes away, and y squared goes away. So now all we have is an x times 3y. So it's 3xy, because y goes into y squared once, right? And leaves one y behind. 3y squared goes into 3y squared equally, and that is just 2. So look how much simpler that was than getting common denominators. All right? Once again, as I said, you don't always have to pick the least common multiple. You could simply pick a common multiple. Where here, I'll just multiply these two values together. So I'm going to do 3 times x plus 1 over 1 times 3 times x plus 1 over 1. I'm able to do this because this is just a form of 1, right? I'm multiplying here, just like I did here. So 3 goes into this, that's left over. Now I have an x squared plus x after I distribute here. And here my x plus 1s go away, and all I have is a 2 times 3, so all I have is a 6, and I'm done. Look how much simpler that was than going through the whole getting common denominators and so on. What I want to do now is show you how much simpler it is. I'm going to take this problem using my LCM method and show you how much easier it is to get to this final answer. So what I'm going to do is erase everything but the final answer and show you how I come up with the same thing. Okay. So, alright, so what is the least common multiple of x and x squared? What value do both x and x squared go into? Well, I could multiply these two together and say x cubed, and that would work. I would have to do some reduction at the end. But I see my least common multiple here is x squared. So I'm going to do x squared over 1 divided by x squared over 1. All right, so I'm multiplying these two things. So that equals 3 times x squared is just 3x squared. Here, x goes into x squared once, so I'm left with a plus 5x, divided by 2 times x squared, minus, here our x squareds go away, and we're just simply with less minus 2. Now look how much easier that was. That took me one step to get here, and I didn't have all the possibilities of not having common denominators. So notice these two things match, which is what we want, right? We want a check and a smiley face. All right. Okay. So I just want to show you that these two problems are essentially the same thing. So let's take this bottom one. So my denominators are 3 and 3 times x plus 1. Now I don't need to multiply these together and go 9 times x plus 1 because this denominator includes this 3. So my least common multiple is 3 times x plus 1. Once again, if you need more help identifying that stuff, here is some very useful videos to help you find your least common multiple and then even a greatest common factor. Okay? Where a least common multiple is what both numbers go into, a greatest common factor is what value goes into both numbers. Right? Okay, so I'll show you all on one page. There we go. So let's consider this problem. I'm going to multiply by 3 times x plus 1 over 1 times 3 times x plus 1 over 1. So right here my 3's cancel. So now I have a 9 times x plus 3 times x plus 1. I'm not going to worry about factoring this out yet, or distributing and multiplying it out, until I see what I get in the denominator. Divided by, here my 3x plus 1's go away. So now all I have in the denominator is a 2. There isn't any reduction we can do, so I would accept this as your final answer, or you could multiply it out and write it as 9 times x squared, 3x, 1x makes 4x, plus 3 over 2, which is equal to 9x squared plus 36x plus 27 over 2. Either of these are correct, but you can stop right here because there was no reduction. Okay, guys? All right, moving along. Let's rewrite. So this thing kind of talks about, is dividing by 3 the same as multiplying by 1/3? Absolutely. And here's an example. 6 over 3 is equivalent to 6 times 1/3. That's simply all it's saying. Dividing by 2 is the same thing as multiplying by 1/2, which we've already kind of seen before. So now let's go in here and do a couple more examples. So here's our example. So 5 and 4, what's their least common multiple? Which would be 20, right? 5 and 4, they both go into 20, so let's just do it that way. 20 over 1 divided by 20 over 1 equals 5 goes into 20 4 times. 4 times 2 is 8 minus 20x, right? Because negative x times 20 over 80. Where all these definitely reduce, they all have a 4 in common. So you get a 2 minus 5x over 20. Right? And look, they're not, this is divisible by 5 and so is this, but 2 isn't. 2 is divisible by 2 and so is 20, but 5 isn't. So that's as far as we can go. You might also notice that if we did a 5 over 5, right? 2 minus 5x over 5, we would end up getting to the same spot. Okay? Let me pick kind of a different one. Let's do this one. So our denominators here are 5x and 5. Okay? Now we have to be careful whenever we do this. Since both of these are constants, what I'm going to do is I'm going to distribute this 10 just so we don't make a mistake in our multiplication. So this is equal to x, and I'll just go ahead and do it to the numerator as well. Okay? Because when I multiply by 5, I want to make sure that I get to both terms, so I'm just going to remove the decimals. So x times 2, so we get 2x over 5x minus 3x, all divided by 10 plus 40 over 5, right? Because 10 times 1 is 10, 10 times 4 is 40 over 5. Now I can do some reduction here. So I get 2/5 minus 3x, because our x's go away. 40 over 5 is 8, and 10 plus 8 is 18. So now I can simply multiply top and bottom by 5. So that equals 2/5 times 5 is just 2 minus 15x. Right, because when I distribute 2/5 times 5, the 5's cancel, all I have is a 2. Negative 3x times 5 is negative 15x. And 5 times 18 is 90. Right? You notice here, 2 and 90 have something in common, but they don't have 15. 15 and 90 have something in common, but 2 isn't. So that's as far as we can go. I want you to know too that this can be written as 2 over 90 minus 15x over 90, and that can be reduced, so it's the same as 1 over 45 minus x over 6, right? Because 15 goes into this one, so it goes in. So these two things are, all three of these statements are equivalent. This one is really the one I want you to leave it with though, okay? All right, so moving along, complex fractions is right here. You have these three pre-class that you have to do with it. This is due 6:13 at midnight. Okay. All right. Now we're going to do some exponents. So we'll deal with exponents and radicals right here. I'll kind of brush on it pretty quickly. This stuff, you know, if you can really understand these rules and how to interpret them, you'll be fine doing these assignments. This is something you want to make sure you do. Make sure all exponents are positive. So we can only combine like terms, and these two already have like terms. So this is the same as x cubed y squared, but this has a negative exponent. What do negative exponents mean? Well, here's an example. Let's consider it the other way. What if I had a to the m? Isn't that equivalent to 1 over a to the negative m? Basically, you negate the exponent to move it to the other side. So since I have that negative in the denominator, to move it to the top, it will become positive. So I can move this y to the top where it's now positive. But I have like terms. I have 2 base y's, so my x cubed is the same. Remember, these are all being multiplied together. There's not 8 y's here. There's only 6, right? Because this is y, that's y squared. And there's y to the 4th. Let's count them. 1, 2, 3, 4, 5, 6. It's y to the 6th. That's another one of our properties. Right here, when we multiply like bases, we add the exponents. The only time we multiply the exponents is in this case, when it's like x squared cubed. That is not x to the 5th, because that's equal to x squared times x squared times x squared, right? 3 times, which is equal to x to the 6th. That is not x to the 5th. Right? These type of rules, if you remember these 6 rules right here, you'll be fine. Okay? Let's jump down. Let's do a big ugly one. Let's do this number 4 right here. I'll leave these other 2 for you guys. If you work on them and you have questions, set up a time in office hours. We can meet over Google Hangouts. We can do a couple things to meet and make sure you understand this material. The first thing I'm going to do here is I'm going to apply, not distribute, I'm going to apply this negative to each of my values. So let's rewrite it first. So x to the first, to the negative first, I need to multiply negative 1 and 1. I get x to the negative 1. Z cubed to the negative 1 gives me z to the negative 3. Y to the 4th to the negative 1 gives me y to the negative 4. All over z squared x to the negative 2. Now I'm going to switch the position of everything to get positive exponents, and then I'll worry about combining them. So this is, all 3 of these are going to go to the bottom. This one's going to go to the top, and the z squared is going to stay. So I'm going to write my x squared over this z squared stays. So notice this value has been put here. This value stays in the denominator because it has a positive exponent. And then all 3 of these are going to go down here. So we get x. Anytime something's to the positive first, you never write the power. If you want, you can, but you don't have to. It's like 10. You don't write 10 to the first, you just write 10. So you're at x z cubed y to the 4th. Okay, now I do have some like terms. Right? I've got these x's right here that I can do some reduction on, and I've got these z's down here that I can do some reduction on. All right? The y is just going to stay there. There's nothing else I can do with it. Okay? So, x squared over x. There's 2 x's here, and I'm dividing by 1. So all I'm left with is 1x. And a nice example of that is right here. This one. So I have a to the m divided by a to the n. Basically, this is going to come up and become a negative exponent. So I have a to the m times a to the negative n, which then becomes this. Right? If this n was negative here, this would be a to the m minus n. So I'm doing 2 minus 1, which is just 1. So in the numerator, all I have is an x divided by z squared times z cubed. How many z's do we have here? We have 5, 2 here and 3. So this becomes z to the 5th, y to the 4th. Z to the 5th, y to the 4th. Okay? All right. There's one more exponent rule, and that is what's called rational exponents. Notice here that m is the same as the power from the previous examples. It stays as an exponent. It's the denominator of the exponent that's important. It becomes the index on the radical. So notice here there's no numbers written. Whenever there's not a number written as the index right here, it is strictly a square root. If it's something other than a square root, it will be specified, like right here, 3, 4, 5. So this is a 2 is here, even though we don't write it. And this is x to the first, even though we don't write it. All right? So this equals, if I invoke this property and go backwards from here to here, I have x to the first, so m is now 1, x to the 1, and my n, my index, my denominator is 2. So this is x to the 1/2. So x to the 1/2 is equivalent to the square root of x. Y, this is my numerator of my fraction, this is my denominator, so it becomes y to the 2/3. This one, it's not written, so this is a 2 right here. So this is x to the negative 3/2, which is actually 1 over x to the 3/2. Remember, you always want to write it in positive exponents. Remember, negative 3 over 2 is equivalent to negative 3 over 2, which is equivalent to 3 over negative 2. Even though this is bad etiquette, you never want to write the negative in the denominator. If both of the values were negative, negative 3 over negative 2, that just becomes positive 3 over 2. Okay, so you don't want to get these two situations confused. They are not the same value. All right? So there's that. So now let's just invoke my properties. So this is my m, this is my power on my x, this is the index, so this is equivalent to the cube root of x. This one is equivalent to the square root, which I'm not going to write it, of y cubed. This is a negative exponent, so I'm going to move it to the top and call it x to the 1/2, which is simply the square root of x. So I can rewrite the square root of x in this ugly form. They're all equivalent. These three statements are equivalent, but this is the best way to write it. All right. It says rewrite using the opposite notation. So you have a homework that's that you need to do with this rational exponents and radicals, and it'll tell you if it gives it in a radical, which is this, it wants a rational exponent. If it gives you a rational exponent, it wants you to write it in a radical. Okay? So z to the fourth root of z to the fourth is equivalent to z to the 4 over 4, which is z to the first, which is simply z. Here, I'm going to get rid of the negative exponent by writing this in the denominator, x to the 1 over x to the 3/2. Remember, 3 is the power, 2 is the index, so this becomes 1 over the square root. I'm not going to write the 2 here, x cubed. This fraction can be reduced. 2/4 is equivalent to 1/2, which is equal to the square root of y. Okay? This one is equivalent to x to the negative 10 over 5, which is equal to x to the negative 2, which is equal to 1 over x squared. Okay? And this one, I'm going to flip where these two are so that they both become positive. Well, first I'm going to show you that this property is possible. You can split the radicals as long as they had the same index. Right, these are both 4 index, so I could combine them under one radical. So now I'm just going to flip the order. I'm going to go the 4th root of y, now y is to the positive 4th. And this is 4th root of x, which is now the positive 2. Y to the 4 over 4 divided by x to the 2 over 4, which is equal to y to the 4 over 4 is just simply y to the first. Make that a little bit prettier. Y divided by 2 over 4th is 1/2. And there it is. Okay? So these are due by 6/13 at midnight. This is the last assignment for this unit. So you have a little over a week from Friday before these are due. So you have plenty of time to get in there, mess around. If you have questions, there's time for me to get back to you. All right, so you have plenty of time as long as you use your time wisely. Okay? And there it is. And this test is due by 6:15, but it's available now. You could get it done tomorrow night if you get all this stuff done. Okay? And then you can move on to the next unit, because I'll start posting videos for this one either later on this week or the very beginning of next week. Also, probably this Friday, I'll send you a paper review of all this stuff, so you have a concrete review right in front of you. Alrighty? So let me save this and close it. So I will post this video I'm making now to the Google Plus online circle. There's a couple students that are in the class. You've probably seen their videos as well. Notice here on my videos I have a summer 1, summer 2. So this is just kind of the order that they're going to go in. So my next video, I'll give you a little blurb what it's about, and then I'll call it summer number 3, last video of unit 1. But this is how I'll keep them in order. Summer number 2, summer number 1. That way you can differentiate them from these other videos that I post. Right? Like this one that says complex fractions. This one is actually made for my face-to-face class in the spring. And as you watch them, if you just look at the time date stamp right here at the bottom, you can tell when it was made. All right? We back up so you can see right here, 128. So I made it last January. So this just goes a little bit more in depth. You notice the values are exactly the same. So I go through, I get the same answers, which is what I want. Right? And there it is. And this is my... Now when I was doing these videos, my mic was a little bit off, so you'll have to bear with the sound on them, but all the information is there. And also, if you want more practice with rational exponents, you go right here to Khan Academy and type in radicals and rational. There you go, exponents, radicals, and scientific notation. All kinds of stuff. Positive and zero exponents. Here's all these other videos. The square root, the cube root, all this stuff to help you understand the material. Alrighty, so you guys are prepared to take this Unit 1 Preliminary Topics exam that is due by the 15th of June. But you want to get that done as soon as possible because you see we have other assignments coming up. Okay? Thank you everyone and have a wonderful day.